Okay, epoxides are seen lots of places. We'll finish up with epoxides here. Vitamin K, blood clotting vitamin. Vitamin K cycle. Vitamin K compound here is going from vitamin K up there to this structure. Is that an oxidation or reduction? Why do you say oxidation? Yes, and gaining hydrogens is a reduction, yeah? Yes. Okay, it's reduced in the body by NADPH. Okay, a reducing agent in the body. We'll mention it later in the class. Then this molecule is called KH2, vitamin KH2, is then epoxidized. That's an oxidation as well. It's converted to the epoxide, and in that process, glutamic acid residues are reduced, and this leads to blood clotting. So vitamin K leads to blood clotting. But then this has to be cycled back. Okay, it's reduced twice back, and it cycles back because you don't have a endless supply of vitamin K in your body. This is an enzyme here that does this. This enzyme is inhibited by anticoagulants. The anticoagulant blocks this step, thus it blocks the cycle, and thus it blocks clotting or coagulation. Basically, I'm showing this because epoxides have a variety of applications, and this is a biochemical application involved. You see epoxide in the vitamin K cycle involved with blood clotting. Lab this week, what are we doing? Oxidation of a diol. Any questions about lab this week? Be turning in your lab sheet from the lab last week when you come to lab, Thursday or Friday. Any questions about the diol oxidation? Okay. Lab tomorrow and Friday. Upstairs, meeting upstairs unless we say otherwise. Epoxides. We'll look at multi-step synthesis. There's other things in this handout. There's a puzzle here. I mentioned it before, right? Practicing epoxide reactions. Synthesis of Prozac, you'll see use of epoxides there. Begin with this alkene alcohol, MCPBA, to get the epoxides. These are enantiomers. The enantiomers are separated. That can be done. What's next? Reaction of this with C to give this. What's the nucleophile in that reaction? I would expect that you have looked at this and have wondered about that question already, right? What's the nucleophile in that reaction? Did anybody come up with that? After that reaction, this molecule is then converted to a mesylate. Remember mesylate with methyl instead of toluene? Tosylate is much more common. They use mesylate, analogous. Okay. What did they use? Probably mesyl chloride, D. What is that? Is that mesyl chloride?
Yes.
Did they use any base?
Looks
Did they use a base in that reaction?
Like
What base did we use with tosyl chloride? Pyridine. What base did they use with mesyl chloride here? Triethylamine. Yes, they use triethylamine as base. Make the mesylate. Then what did they do with the mesylate? They reacted it with what? Methylamine. And the methylamine did what? Displaced the mesylate by SN2. Yeah? And then finally they did an NAS reaction, which is test 2 chemistry, nucleophilic aromatic substitution. We'll learn how to do that on an aromatic ring. So some synthesis there. Other drug application, antifungal drugs, Lamisil, Lotrimin. These work by inhibiting squalene epoxidase enzyme in the fungus. What does squalene epoxidase do? It converts squalene to guess what? The squalene epoxide. Okay? An enzyme in the fungus. And then this continues on into the synthesis of ergosterol, which is an important component of the fungal cell wall. Anybody ever heard of this stuff? You look at fungi in biology classes. Ergosterol, important component of the cell wall that many drugs target, or that the synthesis of that is targeted. Squalene epoxidase is inhibited by drugs such as Lamisil. So you inhibit the conversion of this, you inhibit ultimately the synthesis of ergosterol, and the fungal organism can't reproduce as well. Okay? So, we see epoxides in lots of places, yeah? Synthesis of cholesterol. Or lanosterol. Okay, I think I've already mentioned about aflatoxins. In this handout, there are some questions. These did not make it into the workbook, but here's some questions that could have been. Epoxides. Yeah, I know some of you have been working these because you've been asking questions. And the answer key to that is on the very back. I put it in upside down so you wouldn't accidentally look at it. Okay? There's some epoxide questions. Any questions about those today? We had the warm-up pages. Arachidonic acid. Arachidonic acid is an important precursor to many biochemical compounds like leukotrienes. But guess what? Arachidonic acid is first converted to an epoxide on one of the alkenes. From there, molecules in the body react with the epoxide. Here, the sulfur of the amino acid cysteine reacts with the epoxide, opens it up, nucleophile carbon-carbon OH. Yeah? Have you guys looked at leukotrienes or anything like that in your biology courses? Leukotrienes lead to inflammation, many other things. So epoxides, do they seem important? How are we doing on synthesis? Anybody have a synthesis of the second molecule down here from, what's that over there, from bromobenzene? Anybody have a synthesis here? What's the main functional group? Ether. Anybody have a synthesis? Anybody have a synthesis? Anybody have a synthesis of anyone on this page? Pretty straightforward. Why use sulfuric acid in the last step? Don't need sulfuric acid. Okay. Main functional group is an ether. How do you make ethers? Most common way to make an ether. Okay, so this can go back to what? It can go back to something like that plus that. If we had those two, could we make that product over there? We could also go back to making the ether from the other direction, have the oxygen here, and have something like this. Which one would be best, or would they be equally good? Why is the bottom best? No, there's no resonance with the oxygen. They're equally as good. The halide is on primary carbon in both examples. Right? You can do either one. Okay? This is the one with the benzene ring. Let's keep working back here. What's a way to make an alkyl bromide? Go ahead. Yeah, from an alcohol. You can also come from an alkene. But the alcohol would be this essentially. If you put an H, it would be alcohol. And the alcohol, you can convert it to that. But if you had the alcohol, you could also just do this. I think I would just go with the alcohol. That is, this is essentially, can't we back this up to the alcohol? If you had the alcohol, how would you convert it to this? Yes, sodium metal. We did it in lab one day last week. Yeah? And then you react that with that. Yeah? Okay, how do you want to make the alcohol? Didn't we already make that alcohol in the above example? Did we already make that alcohol in the above example? I think the answer is yes, right? Yes. Can we make it in the above example? Yeah, it's up there at the top, right? You just take the alcohol we made in the above example, and instead of oxidizing it to the carboxylic acid, you do a Williamson ether synthesis using it. Yeah? So this was already done. But Olivia, there's no acid needed here. Acid would put the H back on and you would come here. And by the way, you're right. If you react the epoxide benzene with ethylene oxide, you'll get this directly, and you don't want to protonate it. If you protonate it, you got to turn around and remove the proton. You don't need any acid. And you use the chlorine here. I would use bromine or iodine. I mean, that's just practical because ethyl chloride is a gas, very hard to use. Ethyl bromide is maybe also be a gas, but that's it works on paper. Okay. Any questions about the ones below? Okay, there will be multi-step synthesis on the test. Any other questions about multi-step synthesis?
Does it have to be retro like this, or can we actually just start with bromobenzene and get, or like, does it matter which way we go on the test? As long as like the steps all are included?
It doesn't, no.
Okay.
What's the purpose of retro synthetic analysis? It makes it easier.
That's my brain. I'm not sure.
It makes it easier. So if you want to make it easier, I would do retrosynthetic analysis. Doing synthesis, you need to go back one step at a time. If you just stare at bromobenzene, it can be very difficult. Okay. One step at a time. If you're looking to make the product, it has an ether. How do you make ethers? We use an ether synthesis, so we backed it up to this. Now it becomes, well, how do you make this? Well, nucleophile carbon-carbon OH, so we can back this up to nucleophile, such as phenyl magnesium bromide, which is phenyl anion, plus, what's that? So this backs up to that. Coming forward, we reacted. If you want to put the proton on, you have to first react it, and then you have to work it up. So you have to indicate some appropriate workup. And at this point, well, how do you make phenyl magnesium bromide? Well, you can start with bromobenzene and react that with magnesium. At this point, you see how you just get there. But to just stare at this and say, how do I make the final product, that can be more difficult. Indeed is. That's why going backwards is a thing to do. It's very common. Retrosynthesis. Okay, we need to look at oxidation of alkenes. Guys, I have to have questions from you. If not, I'm plowing ahead. If you don't want to ask questions, we'll plow ahead and we'll have tests, okay? I expect you, when you arrive, you have questions, you have done your homework, and you're ready to go, yeah? Everybody good?
Are we going to talk about NMR stuff today?
If you have questions?
I do have questions.
What questions do you have about NMR?
The integration stuff feels super vague. I don't entirely understand how that all
Okay.
works, like it just
I
feels rather
assume you have
ambiguous.
watched the video,
I have,
and it was
and I've
not,
worked through some of these problems.
integration was not clear in the video.
It just feels kind of ambiguous, like it's kind of unitless. I think maybe that's why it feels ambiguous. I understand what it means, but when it comes to measuring them ourselves,
Certain page in the handout.
let's see, we had to measure, that one was the yeah, so, I don't know what page this is.
Near the back?
Yeah, one of the problems that we had, I don't know if that's helpful, there's not a page number on it. Problem 24 and 25 in Brewis, it says we're not using that textbook, but.
This here.
Yes.
Was this problem done in the video?
Yes, I think what my question is though when we're like measuring those and we're having to find how many H's, like, it's just so unitless. So I'm like, how do we know if we're measuring it right or getting the right proportions or the right things, or, because some of it, like, I would do it differently than you did and then I'm wrong. So, I think that's why like it feels ambiguous and I'm not sure how else to.
You're talking about integral lines. These are integral lines here.
Yes,
That
all of the
give
integral
you
lines.
the area under the curve, the integration, the area under the signal. The signal, the area under the peak is equivalent to number of hydrogens.
Right.
Not like in IR. IR gives you nothing about number of hydrogens, but in proton NMR, yes. And this goes up from here to here, and then from there to there, integral line. And this goes from here to here, goes from there to there, which looks identical, there to there. So you need a ruler. Or if you get good, you can start not needing a ruler as much. Okay? What is 1H or whatnot? Well, if that's 1H there, how many H's is this over here?
1.
So there's my ruler right there, okay? If that's 1, how many is that?
1.
1. Well, how many is this?
2.
Well, if that's
Because
1,
we can't have 1.5.
it looks like 1.5. If we got our ruler out, if that's 6 inches, that's like 9 inches. It's like 1.5. It's not double. You're right, you can't have 1.5 hydrogens. So instead of this being 1 and 1.5, this is more likely 2, and this is what?
3.
3.
Okay.
And since that's 2, this is 2. So now we say that this length is actually 2. You can cut it in half and say that's 1. 2, 2, 3. If that's 2, how many is this?
And that should be 2.
That looks like 2. It's the same length. If that's 2, how many is this?
That'll be
Well,
like
that length is actually the same as that length. So that's 3. And that's the integration because, hey, formula's given.
right.
Sometimes formula will not be given.
Right. That's where I think
We
I
know there's
feel
12
especially-
H's. And here they are. 2 and 3 is 5, 7, 9, and 3 is 12. And so we now see all 12 H's.
So if we're not given formula, how do we know if we've gotten it right?
I had it right before I even noticed formula up there.
But it just
How
feels
do
like
you know
there's
it's
no,
right?
yeah, like that feels so like unguaranteed. Like, well, best guess if there's no
Okay,
formula.
how would you, what are your suggestions of the numbers could have been otherwise?
I have no idea. That's why I feel a little bit like,
They could be double. This could be 4, 6, 4, 4, and 6.
right, how
You
would
can't,
we know?
you can't tell. It's like an empirical formula.
Okay,
It's okay. You can't tell that. It could be 20, 30, 20, 20, and 30. It's really a relative ratio that you were determining.
okay,
Okay? But that's not going to hurt you.
okay.
Okay? If we do, okay. What region is this here in the NMR?
Your area,
Aromatic. And what's the most common aromatic ring?
benzene,
Benzene ring. And did I say it in the video? If you hear horses, think what?
horses. So you
If
hear
you hear
hooves,
hooves
horses.
coming down the road, you think, what's coming down the road? Zebras, antelopes? Most likely horses. Yeah? Go with horses first. Go with benzene first. Benzene ring, right? How many H's on the benzene ring? 5. Thus, how many substituents, non-H's? 1. Okay? So that right there tells us we have a monosubstituted benzene ring. You actually do not have to look at the splitting. I mean, why look at the splitting? The integration, and you already see that it's got to be that.
So that's why in the video you just did the whole piece and you didn't watch it.
Well, sometimes when peaks are on top of each other, the integration is just singly integrated. Because you can't separate that out. The instrument doesn't know. If it's like this, then you can integrate each, and it could be like 2 or 3. But if they're all on top of each other, you just have to integrate the whole thing, and maybe it was just 5. Okay? I can get that from that. Now the rest are saturated CHs. Aromatic region, alkene region, saturated CHs. Okay? 2 here. Okay? Again, let's think horses. This is most likely a CH2. It could be 2 CHs that are identical, but that's going to be more rare. CH2, and this is most likely a CH3. This is actually a very easy interpretation.
Right. That part I got.
Okay? And how do you put those together? There's only one way to put those together. It's a propyl group. Again, you don't even have to look at the integration to get this answer. Okay? Now we can go back in and do that, but basically this here is propylbenzene. Now please don't think they're all going to be this easy. This is an introductory look. Okay? But what is a peak here? What is this peak? It's a triplet, right? Triplet, that's my T. Triplet 2H. That's how it will be written on my NMRs that you see, like in the workbook. What is this? Multiplet 2H. So this has to come from, if nothing has been done for you, you have to say, that's a multiplet. How many H's is it? Well, we already did that. That's why it's called a multiplet 2H. What is this? It's a triplet, yeah? How many H's? Okay. So this would be sort of assignment. We come back here. Let's look at this. Is it really this? What would this be in the NMR? That's a CH2. Would it be a doublet? Singlet, doublet, triplet? What would it be? Yes. Triplet 2H. We have. What would this be? Multiplet 2H. Why is it a multiplet?
Because it gets split by these H's and by those
It's
H's.
split by two. It's a complex split. Okay. How many lines is it exactly?
12 or something?
This splits it into what? This signal, because of the CH3 over here, is a quartet.
Right, so we'll split it into
Okay.
4.
But then this splits each line in the quartet into what? Triplet. So each of the 4 lines becomes 3, and you end up with a total of 12 lines. What do you call a 12 line? A octa something yet? We just call it a multiple. Theoretically, it should be 12 lines. Do you actually see all 12? No. Because some of them, all 12, they're kind of on top of each other. And it may only look like 6. Because this one is just right on top, and you look, it's just one line. But there's directly 12 lines there. Okay, question?
When you're doing that, how do you know which side to start with splitting it up? Like, how did you know to start with
You can do either side. I could have said another triplet, and then each line of the triplet became 4, because quartet, 4, 4, and 4 is 12. Either side. And then what is this going to be on the end here? 2H neighbor, n plus 1 is 3, triplet. How many H's is here? Okay, all the peaks are there. Which of these three are going to be more downfield? This way's downfield, yeah? Okay. All right. Everything in the handout, the terminology is important, okay? Downfield. This is most downfield because it's closer to the benzene ring. Okay, positioning. We said benzylic is going to be about 2 to 3 or so ppm. Okay. Peak position, splitting, integration. These are all topics. Did I do this within the video?
You did. It just was that integration that I was scared that I wasn't going to get the right number of hydrogens, but it's just empirical formula, so it's your lowest numbers anyway, so we're good.
Uh-huh. The main thing is you see it has to be, instead of 1, 1, and 1.5, it's 2, 2, and 3, because you can't have 1.5
Right.
hydrogens.
So you just double it till you get to whole, or you just find your like
Yeah.
nearest whole number.
Now your textbook chapter will give you some little formula to do that,
Okay.
but that'll just make it more confusing because just do it the way I did. Did I use a formula? No, I kind of just use a more common sense approach. All right. Half the time you guys spend your time figuring out what formula means. That's because it's turned into just math and there's no common sense there anymore, and that's the problem. All right. We just have to ask, okay? Because I don't know what trouble you're having. All right. And ultimately, you guys are the ones who need to learn this, not me. All right. Question.
I don't understand how to convert the parts per million to Hertz.
Parts per million to Hertz. I probably did not do that in the video.
You did not.
Okay. Parts per million, ppm. That is the baseline. Why? Did I explain why?
I don't think so.
Where's that at in here? It asks you to do something, right?
Yeah, there's one that gives that you asked us to do that on. It
Page
gave-
numbering would help.
Yeah.
Signal splitting.
17.
It's right
Oh,
after.
okay. It's there.
It's after
Okay.
coupling constant.
Coupling constants. Coupling constants, yep. Down here at the bottom, determine J value in Hertz for the most upfield doublet in the NMR in here. I shouldn't have gave you that. Most upfield, you should be able to look and see that it's the peak at 7.02 ppm. To convert ppm to Hertz, see your textbook. Did your textbook discuss converting ppm to Hertz?
I just don't understand. I need to hear it in order to understand it. I just
Okay,
want to
but
see
it was in your textbook?
It was, right? I can't remember.
Okay. Okay. The most upfield doublet, is that right? Upfield is which way, left or right?
Right.
Right, correct. Upfield. A lot of students think upfield is this way because up sounds like a higher number. No, this is actually downfield. It has to do with, in the old days, you used to turn the magnet up or down, the strength of the magnet up or down. And to get these signals to show up, you had to turn the magnet up. Okay? It doesn't have to do with ppm number. Okay, so, most upfield doublet. Well, none of these are doublets. That's a doublet. Do we see how it's a doublet? See, this is a modern instrument here. It's going to label it like this, but that's actually a doublet. That's a singlet, one. You have to trust this, okay? If that was 2 peaks, I would have indicated it, or the instrument would indicate it. That's just one line Let's solve it. One line, one line. See, those are all singlets. There's your first doublet, or the most upfield doublet. Okay. The coupling constant is the distance between the lines. What's the distance? It's right there in ppm. It's 0.012 ppm. That's the difference. That's just big number minus small number. Okay? That's the coupling constant in ppm. 0.012 ppm. The coupling constants are given in Hertz. So how can we convert ppm to Hertz? You just multiply it by the operating frequency of the NMR. The operating frequency is 300 megahertz. Okay? See indicated up here?
So there's no need to convert from megahertz to hertz? Your ppm is your hertz per megahertz. That's how you get parts per million.
Yeah,
is your ppm, is your hertz per megahertz.
Yeah. What is ppm? 1 per million. Look at the units here if we do this. Ultimately, that's how you do it. Okay. But what is that? What are we really doing there? ppm equals parts per million equals what? It really equals hertz over megahertz. And that's 1. That's like 1 over a million, right? 1 hertz over a million hertz. That's what a ppm is. And the hertz is, well, that's actually, now you got 3 variables potentially. Now we just solve for this. We know what ppm is. ppm is what? 0.012, right? That comes from the distance in your line distance. This equals what? Hertz. That's actually what we're trying to solve for. What is megahertz in this situation? 300. Now, math is a prereq to organic chemistry, so you can be able to do stuff like this, okay? All right? How do you solve for hertz? Multiply both sides by 300. So if you do that, that becomes that, and you multiply this by 300, and that equals hertz. But that's what we did, right? I told you to just, somewhere I didn't I just tell you, yeah, times 300? Okay.
Is that supposed to be 1 over 100,000 or
That's I need another million. Yeah, million. Yeah, 1 over a million is a ppm. Now, why do we use ppm and not just? Why not just plot hertz, which is a frequency? By the way, what do we plot in IR? Reciprocal centimeters, which is a wavelength, but it's reciprocal. Basically in IR, you're plotting wavelength, but you plot it as a reciprocal. And that's all the numbers you learn. Carbonyl at 1700. Well, the wavelength is actually 1 over 1700. And you can convert that to a wavelength. And what do we plot in UV vis? Wavelength, like 600 nanometers? Wavelength. What do we plot in NMR? Frequency. Because light has 2 components, wavelength and frequency. But in NMR you plot frequency. But you don't actually, and what are the units of frequency? Hertz. Okay? But we don't actually plot hertz because it varies depending on magnet strength. If you have a signal at 1 pp, let's do this. I think this is done in the video, so I'm really wasting your time. Let's say you have a signal at 60 hertz. Okay? We could have 60 up here. We don't plot that. Because this is dependent on magnet strength. And I showed that. Okay? There was a diagram that went like this. And the bigger the magnet, the bigger the gap. Okay? And this ultimately comes from that gap. If you use a bigger magnet, this signal may be at 90 Hertz. But it can be the same exact compound, you know, the structure we drew with the propyl. What if I said this was 60 Hertz on that magnet, but over here it's 90 Hertz? You'd be like, well, what's the answer? And then you do another magnet, maybe it's 100 Hertz. That'd be very confusing. There should be kind of one answer. So what was developed is, because this varies, let's divide this by the magnet. Now the magnet, let's say the magnet is 600 megahertz. Now that's the operating frequency for proton. It's also rounded off. Okay? But that's the convention. And this math is what? No, let's call it 60 megahertz. What's that math?
It's 1 part per million.
It's 1 parts per million. 60 over 60 million. 1 ppm. Now over here, this signal is higher because we used a larger magnet. And so the magnet is going to have a larger operating frequency. And it turns out that it would have to be 90 megahertz. Larger magnet led to larger signal. Well, do the math. What does this come out to? Yes, you see they both come out to this. Now everybody's getting the same answer. And you don't have to worry about what size magnet did I use. And so it's a consistency, and that became the convention. So things are, instead of plotting this, which can vary, we essentially normalize it. And ppm, which does not vary, no matter what magnet you use.
Your ratio is going to be constant.
Yeah. It's normalized. If you remember, we normalized when we did polarimetry and organic 1. It's essentially normalizing it. Okay, so that's ppm, and basically, once you do the math, you get 3.6 Hertz. And J values are presented in Hertz. I don't want to explain why. It's not worth explaining why. I can't explain every little thing, but that's just kind of convention. Also, J value, here's ultimately, J values don't vary depending on magnet. So there's no need to have it in ppm. You could do it in ppm. Maybe you can't. Maybe it has to be done in Hertz because it doesn't vary on the magnet. In any event, J values typically are given in Hertz. And it's a direct conversion, okay? Because here's your formula. If you know 2 of these, you can solve for the other, right? But ultimately, just know ppm times operating frequency is going to give Hertz. But it goes back to the formula. Did we get it?
Yeah.
What were you missing?
Why we weren't converting from megahertz to hertz.
Megahertz is the operating frequency of the instrument.
Yes.
Why? How? Well, you got to keep digging at it. We can't address every little tidbit. It depends on what you want to dig at. So that's a J value. It's the difference. Okay. Each doublet, it's very common to determine J values of doublets. Other questions about NMR?
Would we ever have to determine the J value on a triplet?
Theoretically you can, but I would just do doublets. I mean, with triplet, you've got 3 lines, and so, well, theoretically, you could do two J values. I mean, you can just do J value between here and here, or you can do J value between here and here. it's just a distance between your lines. I mean, that's a ppm difference. Because if ppm, if that's 1, 2, 3, 4, you're never going to have a triplet this wide. But the difference between here is 1 ppm. And the difference between here is 1 ppm. But again, can you turn 1 ppm into Hertz? Usually you do J values and doublets. Mainly because it's most informative looking at doublets.
How do we know if one of our peaks is the solvent? Will it just be like massively large compared to everything else?
I gave you a sheet that showed some common solvents.
Okay.
Let's make sure you
NMR.
have seen that. And then we could see what type of questions you have about that. Very back page, yeah.
Okay.
Have you seen that?
I did not see that yet. Nope, I'll look over that.
Look over
Okay.
that, and then we'll see if we can answer any questions about that. There will be solvent and NMR. Most typically, you also see water peak. But I'm sure when I went through, at some point in the video, I hopefully and no doubt mentioned that type of stuff. But again, you can always ask for more information, clarification, and examples. But everything is mentioned in the videos. I can't remember exactly what problems I worked and did not work. I can work.
This last one, you didn't ever work, the one right before the carbon 13 NMR, you didn't ever work in the video. Or maybe you did in another one,
He did.
Okay.
In the last video.
but, okay,
Yeah, he did go over that.
okay.
There's another one he didn't go over, and then there's this series of guessing how many signals there were.
This is the one right before carbon. Did I work that one?
You did. You
Yeah.
worked that
Okay.
one.
I'll find it.
Yeah.
There was another one that you didn't work.
Okay, we're out of time today, but we can continue this as needed. We need to look at alkene oxidations. There's also NMR problems in the workbook, like you'll see on the test. Alkene oxidations will be our last topic. Okay, but we got to really hit that on Friday. That will include ozonolysis, which some of you saw in Organic 1. I don't cover ozonolysis in Organic 1. So that'll be new for my guys that had me. Basically, oxidation of alkenes. Ozonolysis is cleavage of alkenes. Okay? See you guys, some of you in lab tomorrow. Have a good day.
I'm gonna move it. Let me pick this thing up and move it. Watch. See, I moved it. I'll move it again.
feel like I haven't been in this house forever.
Pick it up and move it. I tried. Pick it up and move it. Pick it up and move it. It was already there. It's over here.
Where'd your AirPod from? Are you okay? What happened?
You gonna buy it again?
Wait, you have Patel?
No.
No.
Christy? Cromer?
From
Oh, he's in Cromer. How'd y'all do on the chem lab?
the lab. I got a 92.
Oh, did you get all the points on
I didn't see
the
the
pre-lab?
grade. I don't think so.
Yeah.
I didn't look at the grade.
I made like an 80 on the pre-lab.
Oh wait, then I don't know. I don't know. I just saw this morning just say 92, but I didn't look.
I mean, you should have known like last week what you got.
Remember mine.
We're just supposed to take notes.
I'm about to look right now.
We're just supposed to take notes.
What's wrong? You want to talk to me?
Yeah, I fucked
After?
up on the pre-lab.
I'm happy you got your AirPods.
I just don't
We gotta do one.
They're so
We
tiny.
gotta do one today.
You want to put it? So they're noise canceling. So put this one in. Well, no, they're
Qualitative
completely clean.
analysis.
So be aware of like what you're hearing around you.
I was like, oh, that's why you heard. Which ear does this go in?
Your that one. Did it make a noise?
No?
Has it made a noise yet?
No. Oh, no, it did.
No, I'm gonna put this one in.
I have AirPods.
Sorry for
So
bothering you.
cool.
What'd you do?
You blasted it.
Wait, it's gonna play as soon as you put them on. And then, like, come on. Now you can hear the surrounding.
Oh my god. That is the craziest crap ever.
Noise cancellation.
That is crazy.
That scared me. When
This
I
is
first-
scary.
I
I
had
have
like
to
a
get
heater in my room and I put them shits in and I was like, where the fuck did my heater go? Because now I'm like, oh, it's still on.
Am I talking too loud right now?
The noise cancellation isn't on.
What?
The noise cancellation isn't on.
Okay, wait, it's like half on, half off.
No, it's not. Because you're listening to music.
That is crazy.
You hold it down, the button. Just slightly press it.
That is the craziest shit. I'm getting some. You just sold me. That is crazy. Because I was like, they're too expensive, they're overpriced. That is crazy. Oh my god. Wait, how much did you pay for
They
it?
just go.
I know, it's so scary though. Oh my gosh, if I had money, I would let him Oh, you have a case?
I only really shop for them anything when I'm sad. And when I get really sad, I spend a lot of money.
You know what? I'm gonna say this. If I do well on my mini exam tomorrow, then I'm gonna
Tomorrow?
Yeah, I have a mini exam tomorrow. Wait, how much is yours worth?
We got one today.
Huh? It's when?
Today.
No, it's not. Is it really?
Yeah, it's really. You sit in front of me.
Cool.
All y'all are in the same class. That's so cute. How much is yours worth?
don't remember.
That'd be great. My mini exams are like 7.
But the mini exams are like, they're not as much looking.
How do y'all like Cromer?
It's okay. It's good.
Do you have Cromer too?
I sent him an article last night.
Oh, I have to tell.
What is your name?
Jasmine, what's your name?
My name is Sean. I sent him an article last night.
You sent an article?
I sent him an article.
Oh, I don't have Cromer.
Oh, okay.
Yeah.
All right, so for the rest of you, I was the guy who was in the back. I don't know if you're in the same time slot as I am. I know he is.
Yeah.
But I was in the back, and he was saying something, and I remembered that I had run across some material to the effect that seizures and other metabolic stress-induced neurological disorders could be the result of behavioral atavism. Okay? And so I was explaining that. And then I didn't explain it very well because I have an articulation problem. Like, I'm that moron who gets A's and B's.